Welcome to the third video in the Combinatorics series. Let's start by defining two extremely important ideas: the idea of a set and the idea of a permutation. Now, these two concepts are surprisingly simple, but I can promise you that investing in understanding them clearly will pay dividends in the future. So much of why people find combinatorics hard is because they don't have a clear idea of what these words mean. Okay, so let's make sure that we agree on the definition very precisely. So a set. What is a set? A set is a collection of distinct objects. Usually those objects in the context of math are numbers, so you might have a set S which is equal to, maybe it has the numbers 1, 2, and 3. It doesn't have to have numbers though. You can have a set of letters like A, B, and C, and D, or you could have a set of people like you and me, or you can have a set of colors. You can have a set of pretty much anything. But there's two things that define a set, or two things that make a set a set. The first is that there is no order to the elements in a set. So if instead I wrote 2, 1, 3, in fact, those would be the exact same set. Okay, so sets do not have an order to their elements. That's very important. The second thing is that there are no repeats in a set. Okay, so you're allowed to write repeats. So you're allowed to repeat the number 3 like this, but you just need to realize that you're not changing anything fundamentally about this set. These are all the same exact set. If you put a number in the set once, it's just in the set. It's not in the set any amount of times, okay? A permutation of a set is an ordering, and already we're different than a set, right? Because a set does not have an order, a permutation does. So a permutation is an ordering of some or all of the elements of a particular set. Okay, and again, there are no repeats allowed. So you could order all of the elements if you want. So I can take these elements and then order them in increasing order. So 1, 2, 3, that is a specific permutation. Specifically, that's called a 3 permutation because it's using 3 of the elements. And also I can have the permutation 2, 1, 3, which is another 3 permutation. And these are two distinct permutations, whereas these are actually the same exact set. So, I'm highlighting the fact that a permutation has order and a set does not. Okay. Also, a permutation doesn't need to be of all of the elements in the set. You can have a 2 permutation, which is a permutation of 2 things. So something like 1, 3 would qualify as a 2 permutation. You could also have a 1 permutation, which is just one thing, like 3. And a question that you often answer in combinatorics is, how many k permutations are there of a set? And usually the question isn't posed exactly like that, but it's your job to recognize that it's really that question in disguise. Here's a relatively simple question. Let's say 10 people run a race. How many finishing orders are possible? Well, for the first person to finish, we have 10 choices. And regardless of who that person is, there's 9 choices for who the second person can be. And there's 8 choices for who the third person can be, regardless who the first 2 people are. And this continues all the way down to the last position where we have only 1 choice. So there's 10 factorial different orders here. For medaling outcomes, we only care about the first 3 positions then, right? So for gold, we have 10 choices for who that can be, and regardless of that, 9 choices for silver, and then 8 choices for bronze. So the answer is 10 times 9 times 8. Now, all right, here's a more general question. Let's say we have some set A with n elements in it, and let's just say the elements are called 1 through n. How many n permutations are there? Well, using the same logic as getting 10 factorial in the last question, it should be clear that the answer here is n factorial. What about this question? How many k permutations are there, where k can be any number that's less than or equal to n? Well, the first thing I should point out is that this is a very, very important question to master, because all sorts of combinatorics problems will have finding some k permutation as a part of the process of answering it, right? It's not going to be in every single problem, but you'll soon find that this is a very pervasive quantity. So we might as well develop, a systematic way of doing it. So the good thing is we already kind of have one, right? So the first option, we have n choices. For the second option, we're going to have n minus 1 choices. For the third option, we're going to have n minus 2 choices, all the way until the kth option. How many choices are we going to have? Is it n minus k? Well, students often say that it's n minus k, but in reality, it's not n minus k because, well, if you think about it, that's our first choice, right? And that's our second choice. But it's our second choice, but we're subtracting 1, not 2. And this is our third choice, but we're subtracting 2 from n, not 3. So really, we're going to be subtracting not k, right? So this is our kth choice. We're not going to be subtracting k. We're going to be subtracting 1 less than that, which is k minus 1. And when you subtract k minus 1 and you distribute the negative, you actually end up getting n minus k plus 1. So that's actually the answer to our question. Now, that's a kind of an ugly formula, and honestly, it's not even worth remembering because if you just do it out every time, you're going to get the right answer like we did with 10 times 9 times 8 in the last question, right? Last time we got 10 times 9 times 8, and we didn't really need to think about, well, what's n and what's k? You kind of just did the question. But it turns out that this formula can actually be cleaned up a little bit. So 10 times 9 times 8, it kind of looks like it's about to be 10 factorial, but it stops, right? It's missing specifically a 7 factorial. So if you multiply this by 7 factorial, it actually turns into 10 factorial. But you can't multiply it by 7 factorial because then you're changing the number unless you also divide by 7 factorial. So if you multiply this by 7 factorial and you divide by 7 factorial, you haven't changed the number, but you have been able to represent it a little nicer, 10 factorial over 7 factorial. So you can do the same thing here. This is almost n factorial, but it's missing n minus k factorial. So if you just multiply this by n minus k factorial, and then you also divide it by n minus k factorial, the numerator just becomes n factorial, and the denominator stays n minus k factorial. So we get a formula that you might have seen before of n factorial over n minus k factorial. That is the answer to the question of how many k permutations there are. In fact, oftentimes the answer to that question is referred to as n permute k. And oftentimes people use various notations to represent that number. Some people use p n comma k. Some people use p n k. Some people use n like this with the subscript of k. All of these things represent n permute k, and all of those things are that quantity. So we've talked about permutations of a set, but what about permutations of a string? We've kind of talked about this before with the word spicy, and we've also talked about how we can map this to a set that has the same characters, and then permutations of the string spicy correspond to 5 permutations of that set. The connection, though, becomes a little bit more mysterious when we think about a string like MIRROR, or mirror. Because if we try to use the set logic, the set of characters is just MIRO, because a set doesn't repeat characters. And permutations of the string do not correspond to any k permutation of this set. So it seems like we need kind of a different idea altogether to find permutations of this string. You might be tempted to say the answer is 6 factorial, by the way, because the answer to that is 5 factorial, right? Because there's 5 letters there, and there's 6 letters here, so isn't the answer just 6 factorial? Take a moment to figure out if you agree or disagree. The reason 6 factorial is wrong is because it assumes that the r's are distinct from one another. If the r's were different colors in this problem, then you could argue that 6 factorial is the answer, because maybe the color of the r changes the r. But in general, an r is an r. And if I switch these two r's, even though you can argue that in some sense I've done something, I haven't changed the distinguishable nature of the result. It's still the same string. So the first thing you got to get in your head is when you're counting permutations in this way, you're really counting distinguishable permutations, right? So if you switch these two r's, you should not count that as a separate string, which you are doing when you do the 6 factorial thing. So really, when you do the 6 factorial thing, you're assuming that you have a character set where the r's are distinguishable. So you have like this r1, this r2, and this r3. But in reality, those are all just an R. So when you're counting permutations of this, you're actually overcounting permutations of this. Let's be specific, right? So for this particular string, for this particular permutation, how many times are you counting this particular permutation when you say 6 factorial? Well, one way that you can order these letters to get to this string is to say mi, r1, r2, o, r3, right? That is one of the 6 factorial permutations, and that's going to lead to the original string mirror. But there are other permutations of these 6 letters that also lead to the same permutation mirror. And that's going to be, for example, mi, r2, r1, o, r3, right? I just switched those two r's. And those are being counted differently in this 6 factorial, but they're not fundamentally different because they're going to lead to indistinguishable results, and we're counting distinguishable permutations. So how many of these are there that all map to this? Well, we can sit here trying to list it all out, but we can also think about it more systematically, right? What's really happening is we're shuffling up the r's in the positions that they are, right? So if we're thinking about this particular permutation that we want to count one time, how many times are we counting it in this process? Well, it basically comes down to how many ways we can put the r's down in those exact slots, right? So that slot can be any of the 3 r's, that slot can be any of the 2 r's, and that slot will then have to be the last r. So there's going to be 6 of these, or 3 times 2 times 1, right? Which is equal to 6. So this permutation that we want to count one time, we're counting it 6 times. If you think about it, what about a different permutation? So this is one of the many permutations. How about a different one? How about the permutation M, R, 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 O, I? What about that one? How many times are we counting this one? Well, let's think about it. Well, can we have one example that gets this? Well, we could have M, R1, R2, R3, OI. And again, we can shuffle up the R's anywhere in those positions, and there's also going to be 6 of these. So the key realization is that when we do this wrong strategy, we are counting all distinguishable outcomes 6 times each. So a quick fix is to start with our answer, 6 factorial, and just divide it by 6, which gives us the actual answer of 5 factorial, which if you do out, you can, and you get 120. This is a very common method that you should do, which is you can count something incorrectly and then think about, well, how many times am I actually counting each of the things that I want to count? And if it's the same number for all of your outcomes, you can just divide by that number. Okay, one final idea that's worth really mastering is the idea of a partition of a set. A partition of a set is basically some way of grouping together the elements of a set. More formally, it's some way of splitting up the elements into non-empty subsets that have no overlap to them, so they're mutually exclusive, and they're also exhaustive, meaning that the union of all of them gives you the entire set. But again, more intuitively, it's just some way of grouping together the things in the set. So if you have this set A, which consists of 1, 2, 3, 4, 5, you can put 1 and 2 in one group, 3 and 4 in another group, and then you could just leave 5 in its own group, which you could represent with this partition here, which is you could write as a set of subsets. And because it's a set, there's no order to the subsets themselves, right? So if I switch the order in which this 1, 2 group and this 3, 4 group are written, it would actually be the same partition. So there's no order to the groups themselves. And beyond that, there's also no internal order to the groups, right? Like this 1, 2 is a subset on its own. So if you switch the 2 and the 1 inside, it's actually still the same partition overall, okay? So based on that, we can also think of this as like a 2, 2, 1 partition. For this particular set A, how many 2, 2, 1 partitions are there? Take a moment to come up with a numerical answer to that question. A 2-to-1 partition requires two groups of 2 and one group of 1. So how many ways can we put together the elements of A into two groups of 2 and one group of 1 where the order of the groups doesn't matter and the order within the groups doesn't matter? So let's try to divide and conquer. How can we group together different 2-to-1 partitions of A into different categories, and then we can zoom into each category and address them separately? Well, there's lots of ways that we can do that, but I think the most natural way is to think about which element is going to be in a group on its own. So in this case, it's the number 5, but it can be any of 5 numbers, right? It could be the number 1, 2, 3, 4, or 5. So in fact, those make for good cases or good groups. So case 1 can be the situation where 1 is on its own, all the way down to case 5, where the 5 is on its own, like this case over here. And then you can notice by symmetry, each of these cases should have the same number of outcomes in them, right? So let's just count one of these cases and then multiply the answer by 5, therefore using, you guessed it, the multiplication rule. So let's just assume we're in case 1. If you're in case 1, that means 1 is on its own, which means that 2 is not on its own, which means that 2 has to be with either 3, 4, or 5. So that means that 2 is either with 3, 2 is either with 4, or 2 is with 5. Now let's consider each of these subcases individually. Okay, so if 2 is with 3, well, that means 4 is with 5. So there's only one partition that leads to, right? So that's only one partition there. If 2 is with 4, well, that means 3 is with 5, and that's also only one partition in that situation. And if 2 is with 5, well, that means 3 is with 4, and that's also only one partition in that situation. So that means all of case 1 actually only has 3 partitions, or 3 outcomes. And just like that, each of these 5 cases has 3 outcomes, which gives us a total of 5 times 3, or 15 outcomes or partitions. The reason that strategy worked so nicely is because A is a pretty small set, and also a 2-to-1 partition is particularly amenable to this strategy. If we had a much bigger set and a different partition, like a 37, 506, 29 partition or something like that, this strategy would be really, really horrible. But there's a strategy that we can use which makes use of permutations, which actually generalizes a lot better to much bigger numbers. So we want to count how many 2-to-1 partitions there are, like this one, of this set. The thing is, though, that we're much better at counting permutations than we are at counting partitions. But maybe we can leverage one to do the other. So if we consider 5 permutations of that set, so permutations of all 5 things. So here's one of them, 1, 2, 3, 4, 5. And we could also add these imaginary lines after the second number and the 4th number, because that's going to help us translate a permutation into a partition, right? Like the first 2 numbers are going to be a pair, the second 2 numbers are going to be a pair, and the last number is going to be on its own. So if we can map every permutation to a partition, which we can, like this, then maybe instead of counting the partitions, we can just count the permutations. Well, if we counted the permutations, well, that would be 5 factorial different permutations, which is way more than the number of partitions, right? Because we just solved the number of partitions. There's 15 of them, and 5 factorial is more than 15. So what's going wrong? Well, this should remind you of what happened when we were counting permutations of the string mirror, which is that, unfortunately, multiple permutations will map to the same partition. Specifically, like this 1 and the 2, it could be a 2 and a 1, and that would actually be the same subset and also the same partition overall, right? So that means that I could switch these 2 things. So this could be a 2, this could be a 1, that could still be a 3, 4, and that could be a 5. And these are 2 distinct permutations, but they yield 1 partition. Are there any other permutations that lead to the same partition? And if so, how many are there? Can you figure it out? Well, I could also switch the 3 and the 4, right? So for each of these choices that I could make here, I could also switch the 3 and the 4. So I could have 1, 2, 4, 3, 5. I could also have 2, 1, 4, 3, 5. Okay, so I'm up to 4. Is that it? Well, if you think about it, you could also switch the order of the 1, 2 group into 3, 4 group, and that doesn't change the partition either. So for any of these 4 permutations, I could actually switch the positions of what's here, and that would actually lead to the same partition. So that's actually 8 outcomes, or 8 different permutations that lead to that partition. By the way, I would encourage you to think about a different partition than that one, and think about how many permutations map to that partition, and you'll find that the answer is the same. And you should be convinced that it's going to be the same regardless of which partition we consider. So we can do what we did before and divide the incorrect count by 8, which if we do it out, that's 5 times 4 times 3 times 2 times 1 over 8. Well, the 8 cancels with the 4 and the 2, and that is indeed 5 times 3 is equal to 15. So this seems like a little bit more complicated, but I promise for bigger sets and bigger partitions, this is way better. Here's the question. A class of 15 students need to get into 3 groups of 4 and 1 group of 3. How many possible final groups are there? Take your time and continue when you have an answer. Okay, let's employ the strategy that we just developed. Instead of counting partitions directly, let's count permutations and then account for the overcounting that results in, okay? So if we're counting just permutations of all 15 students, there's 15 factorial different ways of ordering them. Here's one of those 15 factorial different ways. One way of interpreting a permutation as a partition is we can say the first 4 people in the permutation are in a group of 4. The next 4 people are in another group of 4. The next 4 people are in our final group of 4. And the last 3 people, let's say, are in our group of 3. So based on this permutation, we can figure out what partition it maps to. Well, the partition that we get as a result of this permutation, how many other permutations also give us the same partition? Or in other words, how many ways can we shuffle up this string and not change the partition that we get as a result? Because that's going to be the overcounting factor, which is going to apply to every single partition. Okay. Well, I can reorder these 4 people in these positions in 4 factorial different ways, and that's not going to change the partition, right? And for each of the 4 factorial ways I could order these people, I can order these people within their group in 4 factorial ways, and that's not going to change the partition. And for each of the 4 factorial times 4 factorial ways I can organize these 4 people within their own groups, I can organize these 4 people within their groups and these 3 people within their groups, and none of that is going to change the partition. So that means that I'm overcounting by at least a factor of 4 factorial times 4 factorial times 4 factorial times 3 factorial. And I'm not done, actually, because so far I've accounted for the fact that, there's no order within the groups, but right now, there still is order among the groups, meaning if I chose these 4 people first, right? If I just switched these people and these people, that would count as a different permutation, but that is not a different partition. So, and if you think about it, I could also switch around these 4 people or also these people, right? Any way I shuffle up these 3 chunks of people should lead to the same partition. And there's 3 factorial ways of ordering these 3 chunks of people. So I need to further divide by 3 factorial. So the answer to the question is actually 15 factorial divided by 4 factorial cubed times 3 factorial squared. Make sure you understand every piece of this answer.